we're going to continue on the topic of quantitative organic chemistry. And we had mentioned in the previous lecture, that quantitative organic chemistry deals with the question of which functional groups are present in a sample. And we saw that quantitative organic chemistry could be divided into wet chemistry and spectroscopy. And we spent some time looking at wet chemistry, the various tests for alkenes and alkynes, distinguishing terminal alkynes from internal alkynes, looking at aldehydes, ketones, alcohols, haloalkanes, and so on. And you can do those by a series of chemical reactions. You look for color changes, precipitates, and so on. But the second aspect of quantitative organic chemistry deals with spectroscopy. We're going to look at several different types of spectroscopy. We're going to look at UV visible spectroscopy. We're going to look at FT-IR. We're going to look at NMR. And NMR is going to be both proton and C13. And then we're also going to look at mass spec. So ultraviolet visible spectroscopy. We're going to look at Fourier transform infrared spectroscopy. And NMR spectroscopy, both proton and carbon-13. And then we look at mass spectrometry. And if you ask the purist, they won't say mass spectroscopy, they'll say mass spectrometry. And we'll talk about that in some more detail. Before we get into UV Vis, what I want to do is to spend a few minutes describing what spectroscopy is in general, what we get from a spectrum, which is the readout from the spectrometer, the instrument that does the spectroscopy, and to talk about how a spectrometer works in general. This is going to be a very sort of low-level treatment that does not go into any sort of great physics or engineering, but it's important to get a sense of what spectroscopy is, what spectrometers do, what a readout looks like and what it tells you in general, and also what are the limitations of each technique. So spectroscopy is essentially one of the many light, matter interactions. So light and matter interact in many different ways, right? So matter can reflect light, it can refract light, it can absorb light. So there are lots of ways in which light and matter interact. And of course, it's not surprising that there's an interaction, because really at the subatomic level, there is really no such thing as light or matter. Everything is sort of wave-particle duality. So it's not surprising that light and matter interact. And to get a sense of what happens in spectroscopy, what we want to do is look at what we call the modes of motion. We want to look at the modes of motion. And it turns out that there are 4 modes of motion. There is the translational mode. There is the rotational mode. There is the vibrational mode. And then there is the electronic mode. So there are 4 modes of motion, and let me explain what these mean. So translation involves a particle moving from point A to point B without having to come back. So we can think of particles in a liquid, for example, in a liquid, moving from point A to point B, and from, moving very randomly through the liquid. Or maybe in a gas phase, right? Particles are moving all over the place. Or if I drive, from here to Little Rock or whatever, I'm translating. I'm moving from point A to point B without the requisite of coming back to point A. Okay? So that's sort of free motion of the entire particle from point A to point B. Rotation involves the movement of a particle about an axis. So for example, I might consider if I have a molecule, like say hydrogen. So let's say if I have an H molecule, I might consider that molecule can rotate about that axis, and when it does, it will tumble out of the board like this. Right? That's a rotation. Okay? I might even imagine, so let's call this the y-axis. I can imagine that the molecule can also tumble along the z-axis, right? So it can tumble along this axis, in which case it will do this. That's a rotation. So rotation involves motion about an axis. Now there's also an x-axis, right? And so if I were to rotate, if I were to move about the x-axis, what that would do for my molecule is this. Okay? So there are translational motions, in which if the particle moves, it's not bound by an axis. The particle just moves from point A to point B. There are rotational modes of motion, and those are bound by axes in the x, y, and z axes. And then there are vibrations. And a vibration involves oscillation about a point. So for example, if I were to take the hydrogen molecule again, I might imagine that if that's the center, right, the middle of the bond, that the hydrogen atoms can vibrate in reference to that center of the molecule, right, about the point. So whereas rotations are motions about an axis, or relative to an axis, vibrations are motions that are relative to a point, a central point. So I can have this sort of motion in an HH bond, in a diatomic. So these first three are mechanical motions, right? I move from point A to point B, and I expend, there's the potential energy and there's kinetic energy involved. Same thing is true of rotational and vibrational. We're moving from potential to kinetic and maybe back, right? So while these first three modes of motion are mechanical, there is a fourth mode of motion which is electronic. And in the electronic mode, what happens is particles can absorb energy from some low-level state. Let's call it the ground state, right? So GS is the ground state. And I'll have some particle, let's designate it like that. And it can move from the ground state to an excited state, let's call it excited state 1, and then maybe excited state 2, and so on. And the particle can absorb energy. So I have energy in the form of light. It can absorb the energy. And if the energy of this particle, right, if E, which is the energy of the particle, which is equal to Planck's constant times the frequency of the particle, if the energy of the particle is exactly equal to the energy gap between the ground state and the excited state, right? If delta E is equal to EP, then whatever this particle is absorbs the quantum of energy and is promoted to this energy level. Okay? So that's also a motion, but this motion is electronic. That requires the impinging of a quantum of light, of a photon of light, whose energy exactly matches the energy gap in the molecule, some energy gap in the molecule. The particle, whatever that particle is, absorbs the energy and then is excited and moves from a ground state to an excited state. Okay? So there are 4 different modes of motion that we are going to sort of examine. What's interesting though about these different modes of motion is they vary in a couple of ways. They vary in terms of the energies, the range of energies, and also the energy gaps in the system. So, and this would be a very crude diagram. I mentioned that this is a very crude analysis. So if I have energy on this axis, and I were to examine the energy gaps in a translational, the energy spectrum in the translational mode, they might look something like this. So this might be, let's call it T0, which is the ground state for my translational mode. This would be T1. This might be T2. This would be T3, and so on. So what you find, first of all, is the cluster of energies is very low, and the energy gaps between T0 and T1, T1 and T2, and so on, those are also very small. If I go to the rotational mode, what I find is that they're higher, right? As a cluster, they're higher than the translational. And also the energy gaps are somewhat larger. So this might be my R0, my R1, my R2, my R3. And those refer to the energy levels in the rotational mode. If I go to the vibrational, what I find is that they're higher still, and the energy gaps are also larger. This might be my V0, my V1, my V2, and my V3. And if I went to electronic, I find they're even higher still, and the energy gaps are larger. This might be E0, E1, E2, and E3. So on a sliding scale, what I find is that the energies associated with translation are really low, right? They're really low. And perhaps more to the point, the energy gaps in the translational modes are very small. They are larger, the gaps are larger in the rotational modes, and the cluster is larger, right? The cluster is more energetic. The gaps are larger in the vibrational mode, the cluster is more energetic, and it's even more energetic for the electronic mode, and the energy gaps are also somewhat larger. It turns out that this is important because if you look at the electromagnetic spectrum, and you would have seen this in high school, certainly in Gen Chem, if you look at the EMS, the electromagnetic spectrum, I can have, if I have frequency increasing in that direction, or energy increasing in that direction, because the E is equal to h nu. So energy and frequency are proportional. And by the way, nu, so I can also write this as equal to hc over lambda, right? Because nu is equal to c over lambda. So whereas the energy and the frequency are proportional, the energy and the wavelength are inversely proportional. So while the frequency and energy might increase, as I have this from right to left, then the wavelength will increase. The wavelength will increase from left to right. So if I look at the electromagnetic spectrum, there's a very narrow band in the middle, which is visible light. This is visible light. Right? And that will run from, let's do that. This will run from red to violet. And that's what we can see. Below red there will be infrared, that's IR. Above violet, there will be ultraviolet. So infra is a Latin word for below. So if somebody says it's infra dig for me to do something, infra dig is Latin for it's beneath me, it's below my dignity to do something, right? Infra dig. And then ultra means, it's like hyper, means above. So below red, in terms of energy or frequency, is the infrared, and then above violet is the ultraviolet. Of course, you know that there are others below the infrared. You've got radio waves and so on. And then above ultraviolet, you have X-rays, you have gamma rays, and so on. We are concerned in spectroscopy with this set of radiation, at least for most organic chemistry. We are concerned with the band from ultraviolet to infrared. And as it turns out, we get to, in order to carry out the different types of spectroscopy, we will try to access light in the different packets. So, in fact, I did forget one thing because, well, when it comes to NMR, we use radio waves, which are a bit lower. Okay, so here's the point. If I look at the energies of all of the photons of light, even all the way down here, where it's in the radio wave band, we cannot find a photon whose energy is low enough to bridge a gap in the translational mode. These gaps are so small, right? The delta E's are so small here, right? The delta E's are so small, we cannot find a photon of energy that matches any of the energy gaps in the translational mode. Therefore, there is no such thing as translational spectroscopy. So while translation is in fact a viable mode of motion, there is no such thing as translational spectroscopy because I can't find a photon of low enough energy to bridge the gap. And I made the point that for spectroscopy to occur, the incident energy, EP, must exactly match some energy gap in the system. That is not possible in translational mode. There are no photons of low enough energy to bridge the gap. But there are photons of energy low enough to bridge the gaps in rotational, vibrational, and electronic modes. So while we don't see translational spectroscopy, we do see rotational spectroscopy, we see vibrational spectroscopy, and we see electronic spectroscopy. All right. Well, let's think this through. What kind of light will we need to carry out rotational spectroscopy? And the answer is, well, if I checked all the way down here to try to do translation, and I couldn't find a photon of energy low enough, then to do rotational, which has higher energy gaps, I'll have to move right to left along the spectrum. And it turns out in what we call the far infrared, so this is visible, red and violet, right, red to violet. I can break up the region below red, the infrared, to what's called near infrared, which is the one closer up to red, and then the far infrared, right, the part that's far from red. So it turns out that light in the sort of far infrared region has enough oomph, has enough energy to bridge the gaps between rotational modes. To bridge the gap in the vibrational modes, I'll be using light in the mid to near IR band, right, to bridge those gaps. To bridge the gaps in the electronic modes, I'm going to have to use light in the red to ultraviolet region. In other words, in the ultraviolet visible band. So in other words, I can then say that, so there's no translational spectroscopy, but that rotational and vibrational spectroscopy really both use infrared, or the different parts of infrared. Okay? Right? Rotational is infrared, this is really far infrared, kind of bleeding into radio waves. And then electronic requires ultraviolet visible. Right? Ultraviolet visible. In other words, I can say that electronic spectroscopy is UV-vis spectroscopy. They're one and the same thing. Or UV-vis spectroscopy is electronic spectroscopy. Right? It carries out electronic transitions. In this course, which is intro-organic, we will not concern ourselves with rotational spectroscopy. In inorganic chemistry, and there are some complex parts of organic where rotational spectroscopy is of value. It's much more value in inorganic chemistry, some parts of biochemistry, and just a few bits of organic. But as far as we're concerned, we're really more interested in vibrational spectroscopy and electronic. So I can now say that vibrational spectroscopy is infrared spectroscopy, or vice versa. Infrared spectroscopy is vibrational, or it brings about vibrational transitions. UV-vis is electronic, the terms are synonymous, and electronic is UV-vis. Okay, so what we want to do is get a sense of what happens when something absorbs vibrational and electronic, when something absorbs infrared light and ultraviolet light. And before we get into that, let's just see what are some of the limitations on these. And although we sort of are excluding rotational, I do want to start with that as a point of reference, because we looked at it earlier with hydrogen. So if I imagine, and we had it on the board earlier, so we had the hydrogen molecule, and we showed the axes along which the hydrogen molecule could potentially rotate. So we have rotation about the Y, we have rotation about the Z, and then there's this phenomenon about the X. Now, one of the premises that we will make for spectroscopy, and it certainly is it's a quantum mechanical restriction, is that if we can't see a change when we trigger it, then no change has been triggered. In other words, if we say we're going to put energy in, or we're going to initiate some process, if we don't see evidence of a change as a result of that, then no change occurred. Right? And that makes sense, right? Then no change occurred. If I imagine the hydrogen atoms as two faceless balls, right? And I'm going to go back and use this as I'll use this as a model. Not quite faceless balls, I'll use this as a model. If I rotate along the y-axis, then the motion I will see will look like this. In other words, from your vantage point, you're seeing the right hand H move towards you as the left hand H recedes away from you. At some point it's entirely eclipsed and you just see the front one, and then the back one begins to peep around you again, and so you see this sort of tumbling motion. But you can tell something is happening, right? So if I put in energy that causes the hydrogen molecule to rotate along the y-axis, you can see the rotation, and therefore the rotation is happening. So that's an allowed rotation. If I put in energy to cause the hydrogen molecule to tumble along the z-axis, you see it happening, because the H on the right would suddenly go to the top. The H on the left will come to the bottom. You You see that. And then eventually, the one in the bottom moves to the right, the one in the top moves to the left. So you see this event. Therefore, that's an allowed rotation. But if I try to rotate along the x-axis, and let's imagine this whole pen, this whole marker, was entirely blue, was a faceless blue cylinder with no markings on it, it was perfectly uniform. If I try to if I turn this, you can see it, because you can see the blue, and now the white, and now the blue, and now the white. But let's imagine there were no markings, and I tumbled it this way. You can tell it was rotating, which means it's not rotating. So rotation about the x-axis for this molecule is not allowed. Therefore, you're not seeing that rotation. So for a molecule like hydrogen, like dihydrogen, only two of these rotations are allowed. Rotation about the y, rotation about the z. We can't see rotation about the x, therefore it's not happening. Now, that's very different from a molecule like, say, water. In water, if I tumble water about the y, I can see that. If I tumble water about the z, right, I can see that. If I tumble water about the x, I can see that too. Right? I can see that too, because tumbling it about the x would basically do that. So these two h's would fold over. Right? So that's an allowed thing. So depending upon the shape and the character of the molecule, you could have some rotations that are allowed, others that are not. And the same thing is true with vibration. So, and for that matter, electronic. There are certain what we call selection rules that govern all of these transitions. All right. So what I want to do is to look at vibrational spectroscopy, and we're going to ask, we're going to look at what vibrations are allowed. So if I look again at the HH molecule, or I look at the sodium atom, and I ask for vibrational spectroscopy of those things. Well, if there's a central point in H2, and so I can have vibrations that occur this way, right, for the hydrogen molecule. That's very different from, say, a water molecule, where I can have several different vibrations, right? I can have a vibration that looks like this. So I'm going to elongate the HH bond simultaneously. Or I can have vibrations like that. So I lengthen one bond as I shorten the other. So I can have multiple types of vibrations in those molecules. But a sodium atom is a ball. There is no reference point about which sodium can vibrate, right? See, all these vibrations require two atoms, or a minimum of two atoms. So I can vibrate, right, about this point. I can vibrate along here, and so on. But if I'm an atom, a single atom, I can't vibrate, right? There's no other atom for me to vibrate. There's no other atom that I'm bonded to that creates a central point about which I can vibrate. So I can't do vibrational spectroscopy on atoms. So atoms don't have translational spectroscopy. Atoms also don't have vibrational spectroscopy. Do atoms have rotational spectroscopy? And the answer is no. Because an atom is a faceless ball. If I take a faceless ball and I spin it, so let's say I take a soccer ball, which has black and white pentagons. If I spin that, you can see black then white then black then white. But if I removed all the markings from the ball, all the indentations, all the colors, and I were to spin it, you can't tell it's spinning. Therefore, it's not spinning. That rotation is quantum mechanically disallowed.
So atoms don't give translational spectroscopy because nothing does. Atoms don't give rotational spectroscopy because such rotations are not allowed because you can't see the change. The change is not occurring there. And atoms can't give vibrational spectroscopy because they're single points. There is no central point about which they can vibrate. So the only kind of spectroscopy that atoms give will be electronic. Molecules, polyatomic molecules on the other hand, can't give translational, but they can give some rotation, right? Some will be disallowed, like for hydrogen gas. They can give vibrational, they can give electronic. Okay, all right, so let's look a little at how a spectrometer works. And again, this is a very, very low level scenario. Your textbook will have much better diagrams. This is just a working picture. So spectroscopy requires light. So I'll have some light source. I'll have some light source. Right? So this is my light source. That provides the light that I need to be absorbed when I come back. I'm going to have a slit which allows a single pencil of light to come through. That light goes through a monochromator which will select a single color of light, a single frequency of light. And you know this from Gen Chem or from high school. For example, the different types of light, the different colors of light, if you will, vary in terms of the frequency, the energy, their wavelength, right? So the wavelength for visible light is about 400 nanometers. The wavelength for red light is about 700 nanometers. And so each of those wavelengths is a certain frequency. So we will allow a certain color, a certain frequency, a certain wavelength of light to pass through. So that light passes through my monochromator. It is then split into two beams. There's a mirror here that splits my light into two beams. Right? So I've got a mirror here and mirrors here. Right? These are mirrors that will split the light into two beams. And those beams go into little cells. The light from those are bent again, and they go into a detector. The signal is sent to an amplifier, and then that is sent to some sort of recorder. And the recorder gives you a spectrum of whatever it is, right? All of these things are attached to a computer. Right? So everything is attached to a computer. Alright, so what's happening? Let's say I'm trying to analyze compound A. I will, in most cases, dissolve compound A in some solvent. And I will have a solution of A in some solvent. Let's just call it A solvent. So I call this my solution cell. But in here, I will have just the solvent. And I'm going to call this my reference cell. In other words, I want to sort of correct for whatever absorptions the solvent might have. So I'm going to have A dissolved in some solvent here, and then I'm just going to have the solvent there. So there's going to be a negation of the effect of the solvent. I'm going to cancel the solvent effect. So let's imagine then that I have a compound that has light absorbing groups, and my light absorbing groups are called chromophores. So chromophores are light absorbing groups. And you've met this already in Organic 1. You've met, for example, that carbonyl groups absorb light around, for IR at least, around 1700 wave numbers. Right? So the carbonyl group is a chromophore. You know, for example, the OH group absorbs light around 3400 wave numbers. So the OH group is a chromophore. So a lot of the functional groups in organic chemistry are chromophores. They absorb light, and they absorb light in a very specific region of the spectrum. So you can imagine then that I might have a compound which might have absorptions occurring, and let's pick IR as an example. We're gonna get into that in some more detail. But let's pick IR for example. So if I have, let's say I have this compound. Let's say I have this compound. So, and we'll see in more detail. If I have this compound, I will have the carbonyl at about 1710. I will have the CO at about 1300. I'll have the OH at about 3450. I'll have CH at about, say 3000, 3000, so 3000. 2900, 3000. And that's it. Okay? So let's imagine that I have my light, goes through my slit, and I start selecting light at, say, 4000 wave numbers, right? So these are all wave numbers. So I'm analyzing this compound, and I start selecting light at 4000 wave numbers. Well, at 4000, right? At 4000, the light going into the solution cell will not be robbed of photons, because my organic compound does not have a chromophore that absorbs at 4000. My solvent, if it's chosen carefully, will not have one either. And in any event, I'm going to correct for whatever weird things the solvent is doing. So if I look at the light going into my cells, I'm going to call that I0, which is the initial intensity. The light that comes through the solvent cell and the light that comes through the solution cell should have exactly the same intensities. Right? So I'm going to call this the intensity of the solution cell. This is the intensity of the reference cell. These numbers should be exactly the same, because they both have solvent, so that's a balance that washes out. And A, which is present in my solution cell, has no chromophores that absorb at 4000. So the intensity of the reference and sample cells are exactly the same. My detector measures no difference, and so I get no absorption at 4000. So I have a blank at that level. Nothing happens. At 3999, the same thing happens. At 3998, 97, 3500, blah, 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 blah. Nothing happens, so I just have a straight line which indicates the absorption of the sample cell and the reference cells are exactly the same. But when I hit 3000, my analyte has a chromophore, the CH bond, that absorbs at that value. The reference cell does not. So what will happen is the light going into the solution cell will be robbed of photons that correspond to that energy. And so the intensity of the beam coming out of the solution cell would be lower than the intensity of the beam coming out of the reference cell. The detector picks up the difference and amplifies it. And I see that as a blip. And by the way, the more intense the absorption, right, the deeper is this peak, at least in IR. So at 3000, I would have a band. And then, oh, shoot. Okay, let's call that 3450, right? Because I forgot that one. So I've got my OH group that's absorbing at 3450, right? And then at 3450, I get an absorption for the OH, and then it's a flat line again until I get to 3000. And at 3000, when my CH absorbs, I'll see something. Then it'll flat line again all the way until I get to 1710. For now, let's not bother about how intense the bands are. I'll see something at 1710, then nothing again until 1300, and so on. So basically what the machine does, what the machines do, is they look for differences in the intensities of the light coming out of the solution cell and the reference cell. Any difference is an indication that there's a chromophore in your analyte that is absorbing at that wavelength. The machine then picks up a difference in light intensity, amplifies it, and that shows up, because it's a running screen, and that shows up in your spectrum. What I've just described here, as I said, is a very old version of a spectrometer. This is called a continuous wave. Spectrometer. And even though these devices are not really present anymore, they don't really hang around in most modern labs, it does give you a good understanding of how rudimentary spectroscopy began. And it gives you a good sense of what the machines are looking for. It retains the same idea, but rather than sweep the entire frequency range, we don't really do that anymore. We shoot them all at once. And we'll talk about that in some more detail later on. Okay, so we sort of understand then what the various modes of motion are, why we don't have translational spectroscopy, why atoms give only electronic spectra, and why we don't see rotational spectroscopy or even vibrational for certain species. The last point we make is that if you look at spectra for the different types of techniques, UV-Vis, FTIR, they differ in appearance. What a spectrum gives you, by and large, is a graph of some energy term against an intensity term. That's basically what a graph or a spectrum gives you. It's a plot of intensity which is related to how many of those chromophores are present and how easily they absorb light, right? How well they absorb. Some groups are better than others. And an energy term, in other words, at what frequency, at what wavelength do we absorb? So on the horizontal axis, your energy terms can vary. They can be frequency, they can be wavelength, or they can be wave number. So remember we wrote that E is equal to h nu, which is equal to hc over lambda.
Well, I can call the term 1 over lambda, I can call this nu bar, in which case this becomes hc nu bar. So if I define the inverse wavelength as the term nu bar, then the energy is equal to hc nu bar, right? So 1 over lambda becomes nu bar. So the terms that I find for energy, the proxies for energy, are frequency, wavelength, and wave number. You see wave number in IR, you see wavelength in UV vis, and you see frequency or a modification of frequency in NMR. And on the vertical axis you see intensity. Now, some spectra, like in ultraviolet visible, have bands that are right way up, right? So we say they're positive. Others look like this, like for IR, right? So it looks something like this, right? And the intensity term for IR tends to be transmission, right? And then I'll have wave number at the bottom. So I have wave number here, and if this were UV vis, which is kind of what this looks like, I'll have nanometers, right, which is a wavelength term. But one of the questions we're going to ask and answer is, if I were to run, for example, the spectrum, the electromagnetic spectrum of sodium, what that looks like is this. So if I run a spectrum of sodium, right, sodium vapor or whatever, helium, right, doesn't really matter, what I see is a line spectrum. In fact, if you remember from your Gen Chem, we talked about the Lyman series and the Ballman series and the Paschen and the Fund series. They were all line spectra for hydrogen. But the question is, why is it that the spectra for sodium gas and helium and so on are lines? The spectra for IR are bands, but they're relatively narrow bands. But the spectra for UV vis are broad bands. Why one is positive and negative is really irrelevant. I can change the mechanics of the computer and flip them. That's easy enough to do. But we're interested in why do they look different, right? Why are some lines, why are some spectral lines, why are some sort of narrow bands, and why are some broad bands? And the reason is as follows. So, for example, let's say, in fact, yeah. So let's say I were to take, let's say I were to take some molecule. So this is UV vis. This is IR. And this would be ROT. So I'm going to take some compound. I don't really care what the compound is. And I'm going to run rotational spectra on it, IR and UV vis on the same compound. And what I find is ROT gives me lines, IR, which is VIB, gives me bands, and UV vis, which is electronic, gives me broad bands. Right, so the reasons are actually quite simple. If you remember, these would be the energy gaps in the ROT, these would be the energy gaps in the VIB, these would be the energy gaps in the ELEC. So ELEC, electronic, vibrational, and rotational. So when I do transitions in the rotational mode from R0 to R1 to R2 to R3, I
I'm absorbing a very precise amount of energy to go from R0 to R1, or R0 to R2, or whatever. Very precise amounts of energy. So I'm absorbing only a single photon to do this, which has a single energy, then a completely different energy to do that one. So I will see them then as discrete lines in my spectrum, right? R0 to R1, R0 to R2, R0 to R3, and so on. But because these are discrete, I get discrete lines. Okay. What about vibration? Well, vibrations, each vibrational energy level is now associated with an entire cluster of rotational energy levels. So V0 is really going to be associated with a series of R values. So there'll be an R0, an R1, an R2, an R3, and an R4. Same thing with V1. V1 will be associated with a whole cluster of, V2, a whole cluster of rotational energy levels. R0 to Rn, R0 to Rn. So when I say I do a transition from V0 to V1, I'm really saying maybe I'm doing V0 R0 to V1 R0, but it could be V0 R0 to V1 R1, or V1 R2, or all the way to V1 Rn, or I could be doing V0 R1 to V1 R1, blah, 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 blah. So I'm going to be doing a series of very closely related transitions, requiring very similar energies. So going from here to here would involve going from maybe this to that, or this to that, or this to that, or whatever. And those energy gaps are very, very close to each other. So the machine picks up a series of lines. Each one is let's say a V naught to V1, and the lines are very, very close. The machine can't resolve them, so what it gives you is a band, which is the accumulation of all the transitions from here to here. So I get a band, which really is a cluster of very closely spaced lines. As you might imagine, when I go to electronic mode, each electronic mode is associated with a series of vibrations, or vibrational modes, and each vibrational mode is now associated with its own menu, its own cluster of rotational modes. So when I say I go from E0 to E1, well, good Lord, I could be going from E0, V0, R0 to E1, and just take your pick. So the number of possibilities has now expanded, which means all of those transitions are occurring simultaneously, and really it's just a lot more transitions. So I'll be getting a series of lines, it's a whole bunch of lines, very closely spaced in energy. The machine can't tell the difference, so it accumulates them all into one band. And the reason the band is broader is because there are just a lot more transitions that are very closely spaced. So electronic transitions are broad bands, UV-Vis transitions are broad bands. IR, because they contain electronic, vibrational, and rotational. IR is really vib-rot spectroscopy. So UV-Vis is electronic, but it's adulterated with vibrational and rotational, broad. IR is really vibrational, but it's adulterated with rotational. So it's somewhat broad, not as bad as electronic. The only ones that are pure are rotationals. Because translation, which is next, doesn't give you spectroscopy. So I'm going to get discrete spectra, discrete lines in the spectra for rotation. The last point I'll make, and we had just sort of talked about it a little bit, is that if I look at the electronic spectra for atoms, not molecules, if I look at the electronic spectrum for atoms, like sodium or helium or whatever, what I see are lines. So how is it that the electronic spectra for molecules, right, give me broad bands, but the electronic spectra for atoms give me sharp lines that resemble the spectra for rotation? And the answer is, if I look at an atom, like say sodium, what types of motion, what modes of motion are available to an atom? So there is no spectroscopy for translation, so that's out. An atom cannot rotate. It's not quantum mechanically allowed because you can't see evidence of rotation when a faceless ball spins. You can't tell it's spinning, therefore it's not spinning. So I can't do translation, I can't do rotation. Atoms can't vibrate because vibration requires an external point above which at least two atoms are oscillating. If I'm monatomic, vibration is impossible. So it means the only type of spectroscopy that an atom can undergo is electronic, which means it's not poisoned by vibration or rotation, so I just get discrete lines. In other words, I imagine electronic without Vib and Rot. I imagine electronic without Vib and Rot, and that's single line transitions. Very discrete energy quanta required. Therefore, very discrete lines. Okay, so that's a rough introduction to spectroscopy. When we meet next, we will talk about UV vis, which we'll spend one session on UV vis, and then get into more detail on infrared and NMR, and then mass spec. Okay, thank you.